Okay, I want to look at one application of the DFT, and that's actually using the DFT to compute the linear convolution of two discrete time sequences, or as an approximation to computing the continuous time convolution of two waveforms. And we'll start with that approach. We know that the output of a linear time invariant system can be found by convolving the input x of t with the impulse response of the system. We can approximate these time domain waveforms by sampling them. And again, sticking with the definition in the book of our corresponding sample sequences, we sample the waveforms and multiply by t. This gives us the proper scaling so to be consistent, so that our DFT is samples of our Fourier transform, and similarly h of n is t h of n t. Then y of n can be found by convolving discrete time convolution of x of n and h of n. Okay, so we're going to assume here that x of n and h of n are both finite, have finite duration. So if x of n is non-zero for 0 for n between 0 and n1 minus 1, so we'd say that x of n has n1 non-zero samples, and similarly h of n is non-zero for 0 for n between 0 and n2 minus 1, or in other words, h of n consists of n2 non-zero samples. Then we know, looking at our convolution results previously, we know that y of n exists for 0 less than n less than n1 plus n2 minus 1, or in other words, y of n consists of n1 plus n2 non-zero samples. Well, circular convolution, which is what we get when we multiply the discrete Fourier transform of our two sequences, we can use that to get an equivalent linear convolution result, which is what we're after. It requires that we zero pad our two sequences out to the length of the linear convolution result, n1 plus n2 minus 1. Okay. So the steps in using the DFT to find the linear convolution of two discrete time sequences, or correspondingly to approximate the linear convolution of two continuous time waveforms, we find the discrete Fourier transforms of x of n and h of n, zero padding out to the length of the linear convolution result, n1 plus n2 minus 1. And we'll use the FFT algorithm to actually compute the DFT for us. And then 2, we can then find the DFT of the output sequence by multiplying the two DFTs together, and then 3, we'll find the inverse discrete Fourier transform of y of r to get our desired output sequence y of n.